Welcome everybody. This video will be on gases. The potential upcoming test will include Unit 6 intermolecular forces and Unit 7 gases. I wouldn't adhere too much to this statement. Hot air balloons utilize helium, which is less dense than air, allows hot air balloons to float. Okay, process of utilizing the concept of density. Chemistry joke, this isn't funny to me, but to each his or her own. I'm moving on. Kinetic molecular theory, kinetic motion, the motion of molecules. Anything to the right of the stairs, including hydrogen. Theory, a rigorously tested idea or concept, an overarching idea that is explained through years of analysis to explain some type of phenomena. It goes under these postulates. Gases are hard spherical particles that have insignificant volume. That means if I draw a couple dots here to represent gas particles, the size of the particles are insignificant compared to the distance between them. And the intermolecular forces are basically non-existent, are not attracted to or repelled by each other. A better way of saying it, are neither attracted to nor repelled by each other. There's your SAT tip. Move randomly in straight paths, so they do move randomly in straight paths. So that's not straight, but pretend it's straight. And when it hits and it collides with another gas molecule, it's going to go in a different direction in a straight line. Experience elastic collisions with complete transfer of kinetic energy. Elastic means no loss of energy. I need you to know that. No loss. And when you're playing pool, like billiard balls, you're hitting billiard balls. You're going to hit the 8 ball into the corner pocket or the 14 ball in the side pocket. So when the cue ball and the object ball collide, there is no loss of energy. Now, physics people would argue there's friction. Okay, let's not go there. Now, inelastic collision would mean there's a loss of energy as, say, two vehicles get in a fender bender. The distortion of the plastic or the fiberglass would be where the energy's lost. Okay, instead of moving the cars are stopped and it's gone into distorting the shape of the materials of the car. That would be inelastic. Variables that describe a gas: pressure, that's collisions against a surface. All right. So these are gas molecules. The faster they move, if they have a higher temperature, they're going to create a greater pressure. If you have more molecules too, you're going to have more collisions. So they would create more pressure. So atmospheric pressure is where air molecules collide against the ground, surface of the earth. Volume, the size in 3 dimensions. Temperature, the average kinetic energy of a substance, aka the speed. We use Kelvin after Lord Kelvin. And amount in moles. You know moles. Utilizes N in this unit and another unit. We'll get to that in Khan Academy. How are each of these variables related to each other? Well, we're going to show you through the gas laws. The first law is Boyle's law. After Robert Boyle, it says as pressure goes up, volume goes down. As the pressure goes down, the volume goes up. Equation: P1, pressure 1 times volume 1 equals pressure 2 times volume 2. What is the ones represent initial conditions, the twos represent the final conditions. So this would be the first pressure and the first volume, and this would be the final condition of the pressure and the volume. And here we're talking external pressure. So the more pressure you have externally, the smaller the volume. This is an inverse relationship. Inverse, not indirect, inverse. That's supposed to be an I and an N and a V. Inverse, INV, inverse relationship. The graph shows the inverse relationship between the two variables. Pressure on the y-axis, volume on the x-axis. As one increases, the other decreases. See here, very, very, very high pressure pushing down externally, and small volume, less than 0.5 liters. Here you got a big volume and little pressure. You ought to ask yourself, well, why is the line curved? Why isn't the line straight? My line's not very straight either, but bear with me. Why wouldn't they just have a straight line? Give you a moment to think about that. Pause the video. All right, welcome back, scholar. You should say to yourself, well, it has to be curved because we're going to cross the zero line. And you can't have zero volume, you can't have zero pressure, so you cannot cross the asymptote. So as the volume approaches infinity, the pressure approaches zero, but you can't make this zero. Okay? You can't make the volume zero, you can't make the pressure zero. So how do I remember Boyle's law? Boyle played the violin. BPV. Boyle played the violin. Charles' law. The volume of a fixed mass of gas is directly proportional to the Kelvin temperature when pressure is held constant. So what does that mean? Constant. Any statement that uses the terms fixed or constant will not be used in the equation. Okay. If my pressure 1 is 8 and my pressure 2 is 8, then when I go to divide them out, it's going to be 1. They're not going to change anything. So they're never used. So if it does not change, cross it out in the problem always for Boyle's law, Charles' law, and the upcoming laws. The next two I'm going to cover. The equation, volume and temperature. How to remember that? Charles went to Virginia Tech. Alright, I'm glad I left this up. Charles' law, this graph explains how absolute zero was determined. When they had to, from here, the graph, the variables are volume and temperature. So when they have the volume approach zero, they're able to calculate the temperature at absolute zero. 0 degrees Kelvin, 0 Kelvin. And you don't use the degree sign with Kelvin like you do that little circle. But I'm not going to make a big deal out of it. That's minus 273.15 degrees Celsius or minus 459.76 degrees Fahrenheit. That is so cold. Not even Pluto gets nearly that cold. It's unfathomable. You can't even fathom how cold that is. But you cannot get to 0 degrees Kelvin. You can get to, they've gotten to decimal point, I believe 7 or 8 zeros and then 1 Kelvin. But you cannot remove all heat from a substance. Okay? You will just keep going. You would add another 0.0. You might get 0.0000. You might have 10 zeros and then a 1. But you're never going to be able to get to absolute zero. So that's a theoretical value. But we can get pretty darn close under lab conditions. So it's pronounced Gay-Lussac's law. Gay-Lussac's law. It's French. Right? Oui, oui. The pressure and Kelvin temperature of a gas are directly proportional, provided that the volume remains constant. So pressure, I wanted to ask you, we have pressure and temperature and volume remains constant. Which one of these variables will we not use in this equation? And hopefully you would say volume because it's constant. So we just use pressure and temperature. This is a direct relationship, just like Charles's law was a direct relationship. As one increases, the other increases. As one decreases, the other decreases. So these two are direct relationships. So you see here, if you heat this up, you're here, and then you heat it up, and they start moving faster. Your collisions are going to be greater, and you're going to increase the pressure. Remember, pressure is created by collisions against the surface. So that's since they're moving faster, you're going to increase. And you see how they're proportional. 100 to 200, 300 to 600. That's why we use Kelvin. Celsius wouldn't do that. Celsius would give you negative numbers sometimes if you get too cold as well. So always use Kelvin temperature. Combined gas law expresses the relationship between pressure, volume, and temperature of a fixed amount of gas. So P1, V1, T1, P2, V2, T2. Remember, all the ones are on the left, the initial conditions, all the twos are on the right. Remember, the T's on the bottom. You can remember that. You can remember all the other laws that we covered. The combined gas law contains all the other gas laws. If the temperature remains constant, what do? You say bye-bye to the temperature. Whose law do we have? Well, who played the violin? Boyle's law. So easy to derive the other equations if you know the combined gas law. So PV over T. One's on the left, final conditions on the right. So if the pressure remains constant, I wonder what we're going to get rid of. Of course, the pressure, guys. And who went to Virginia Tech? Oh, our friend Charles. Charles's law. And combined gas law, if the volume remains constant, okay, you're going to get Gay-Lussac's law. Things to know. All temperatures must be calculated in Kelvin. If given degrees Celsius, must add 273.15. Example, if I give you this in the problem, you're going to have to change it to Kelvin before you start doing P1, V1, P2, V2. So you're going to add, just remember, C comes before K in the alphabet. So if you're converting to Kelvin, your number should be getting bigger. You're going to add this number. That's all you do every time. And if you're in Kelvin and you're converting back, just subtract 273.15. That's all you do. So you need to remember this number. It's never going to change. It's immutable. Pressure. Collision of molecules against the surface. Okay. 1 atm, that's atmospheres, is equal to 760 torr after Torricelli, which is equal to 660 millimeters of mercury, which is equal to 101.3 kPa. Just in case you're curious, why would they use mercury to measure pressure? Well, geniuses, it was done many years ago, and mercury, you remember, is a liquid, so that made it very convenient. And they didn't know it was toxic. They can't use water. The density's too low. So if you were going to measure the pressure, you'd have to have an instrument that is, multiple stories high if you were going to utilize water. And of course, water can freeze. That didn't make it a good choice either. mercury is 13.6 times as dense as water. So you could, its fluctuations with varying pressures didn't go up and down as much. So in case you're curious. Okay, these are all equal. 4/4 is equal to $1, is equal to 10 dimes, is equal to 100 pennies. All right, they're all equal. I need you to know them. So if I ask you to convert 3.44 ATM atmospheres, not atoms, to millimeters of mercury, well, this is your given. Remember, ATM, where do we get that one from? We got it from here. So I need you to know that. I think of A1 steak sauce. To remember atmosphere for 1 atmosphere. I remember this 101.3 KPA, your favorite radio station. Okay, yeah, right, but just go with it. Okay, and then your new unit is mm of HD 760. All right, hopefully you can do that, but it might take a little bit before you get comfortable. Convert this one to KPA. Again, put down your given torr, divide out torr to torr. You get torr from right here, 760. So that's never going to change, that number for your conversion factors. Okay, your conversion factors are here. Okay, don't get that confused with the given. The given can be anything. The new unit in the numerator. All right, guys, that was a little bit longer than I wanted it to be, but I think it was pretty thorough. If you need help with the math problems, please ask to set up a video meeting, or I can type them out for you in a post. All right, be well. Check the lesson plan. Stay safe.